Hello and welcome to EENG 658, Introduction to LiDAR Systems. Today's lecture is basically an introduction to the course, where we're going to talk about the history of laser radar and go over some basic sort of concepts of direct detection LiDAR systems. We're going to begin by putting sort of laser radar in sort of its historical context, by realizing that it's sort of a natural offshoot of radar, which is known as radio detection and ranging. And really, it's conceptually pretty much the same thing. Radio detection and ranging applies to any system transmitting and receiving electromagnetic radiation. The early development of radar was spurred on by the competition preceding World War II, where you had England and Germany both trying to develop the technology. Early English systems monitored changes in reflected energy from commercial radio stations and didn't have their own radar transmitter. But eventually, of course, the development of a radar transmitter with a radar receiver, the pair of those things making a radio detection and ranging system, allowed for accurate ranging and detection of targets over the skies of Europe in World War II. Now, the beginnings of laser radar begins really with not laser detection and ranging, but light detection and ranging, which is what LiDAR stands for. And the earliest light detection and ranging systems were cloud height monitors, which were in use by meteorologists by the 1950s. Now, I think the first ones possibly were created even in the 1930s, but the technology really wasn't practical until later. And the way it worked is you would have sort of a strobe light that sets off a high intensity light pulse that bounces off the clouds, and then you have a detector that monitors the amount of time it takes for that light pulse to get back down to the detector, and of course you can get a range measurement that way to a cloud that's laser detection and ranging wasn't really made possible until the laser was invented in the 1960s, and the first true laser radar system was used for atmospheric research. So basically, lasers were used to illuminate the atmosphere, and returns from those laser signals were used to determine the composition of the atmosphere and maybe where boundary layers are or where scattering effects were occurring. So that isn't meant to be an exhaustive history of laser radar, but it gives you sort of some historical context for how the technology began to develop. Of course, once the laser was developed, pulse lasers, better timing, and all the things, and then arrays of detectors, which gives us 3D imaging laser radar. All these things have cascaded to give us the laser radar technology that we see today and that we'll be studying through parts of this course. So next, we're going to move on to pros and cons of laser radar versus classical radar. And we're going to start by talking about the main difference, one of the huge differences between laser radar and most classical radar systems has to do with the wavelength of the electromagnetic radiation being used to do the detection and ranging. And the laser radar system uses a light which has a much shorter wavelength than most radar systems, and so this short wavelength yields high spatial resolution through this equation that we're showing here, what's called the classical diffraction limit. It's developed by Lord Rayleigh. It tells you what the minimum angle that two points can be resolved through when you're looking at them, based on the wavelength of the light that's coming from those points, and where d is the diameter of the optical system that's viewing the radiation that's being used to collect the radiation. So if you have a telescope with diameter d that's viewing light with wavelength lambda, you can resolve 2 points angularly that are separated by delta theta in angle, if they are at least 1.22 lambda over d. And this equation governs both the operation of laser signals and radar signals. And since laser signals have shorter wavelengths, they can achieve a higher spatial resolution, meaning that they can resolve to targets that are more closely spaced angularly or have a smaller delta theta. So putting in some parameters for laser radar systems and a conventional radar system, we see that if we have a radar system that uses radio waves that have a 3 centimeter wavelength, and we use a 1 meter dish antenna to detect the signal, that they'll be able to resolve targets that are separated in angle by 3/100ths of a radian, or about 1.72 degrees. Conversely, a laser radar system using a 1.06 micrometer wavelength of light, which is one of the standard lasing wavelengths, and a much smaller aperture than 1 meter, say a 2-inch lens, can achieve a sort of minimum angular resolution of, that looks like 1, 2, 3, 4, 5, about 21 microradians, or 1.2 thousandth of a degree. So even with a much smaller input aperture, just because due to the wavelength difference, laser radar systems can achieve a much higher spatial resolution, and therefore are better at determining, rejecting signals from background and clutter. Other aspects of laser radar systems is that the short wavelength of the light can allow the laser signal interacts with the atmosphere more readily. Now, this, as we'll talk about in a moment, could be a negative aspect to laser radar, but it also allows for atmospheric sensing sort of what's in the air, because the light interacts with the air particles and basically the constituents of the air path that the light is going through. Now, also, the laser systems produce less multipath problems. And what multipath is, say you illuminate an area and then you get returns from different pieces of that area. If you're illuminating, say, a city with a light beam, you can reduce multipath by narrowing the beam, so you don't see both. You don't get laser returns from the sides of buildings and the ground and other things. You can only get laser returns from the small area that you're illuminating, and that small beam is made possible because the ability to focus a beam into that has a divergence of delta theta is also related to the wavelength of the radiation. So radar beams basically have larger divergence angles, and they have more multipath problems, because when you use the radar to illuminate areas in a city, for example, you'll get bounces. The radar signal may bounce off multiple buildings before coming back to the receiver. Cons of laser radar really focus again on the interaction of the laser radar with, one of the main cons of laser radar is, again, because of its short wavelength, it's more likely to interact with particles and constituents of the atmosphere, which can be a pro if you want to sense those things. But if you want to look through the atmosphere to see more sort of non-atmospheric targets, or targets that are made by man, for example, and aren't just in the air, then the fact that the air can obscure signals by absorbing them or reflecting them makes LiDAR not as attractive as radar, which goes right through the air and, of course, then bounces off planes or tanks or whatever it is you're trying to see. Now, the other aspect of laser radar that isn't very palatable in a lot of cases is that the laser efficiency, or the amount of power you get out of a laser versus what you put in it, doesn't really rival radar transmitter systems, where you can get 80-90% power out of the radar into the radar beam from the electricity you put in it. For a laser radar system, that could be as low as 10%, 5%, something like that. And more efficient lasers maybe 20% or around a number like that. But radar systems are vastly more efficient, which helps with size, weight, and power constraints on aircraft and spacecraft. And that's why radar has been, from a aircraft standpoint, the the system of choice for sensing, what's around a flying airplane or a flying spaceship, for that matter. Laser radar systems have different applications than air defense. So although are scenarios where either system could be used, they're in fact uh, used best when they augment each other and take advantage of each other's strengths and weaknesses. So what we're going to do is sort of some side-by-side comparisons for some applications, just to give you an idea of when one system might be better to use than another. So while a synthetic aperture radar imager can achieve spatial resolution comparable to that of a laser radar system, this is generally only achieved in the in-track dimension, meaning in the dimension that the aircraft that's generating the synthetic aperture is moving. And synthetic aperture radar imaging techniques require that the scene be stationary during the formation of a SAR image. And this limits the size of the SAR aperture, thus the resolution. So when it comes to imaging the ground, it's difficult for a SAR system to be competitive with a laser radar system, except for the SAR system can see through clouds and things like that the laser radar system has a difficult time seeing through. Other ways you can think about comparing LiDAR versus radar systems is LiDAR generally, achieves a higher spatial resolution, but it's at the cost of limited range. That's what limits the range of a laser radar sensing system is how much atmospheric path it has to go through. And of course, it has a difficult time scanning the same volume for the same amount of input power because of the efficiency loss due to the fact that you just can't generate as much laser power for the same amount of electricity as you can generate radar or radio wave power. But LiDAR does avoid multipath problems that are encountered in SAR in urban environments. And so, although the research into solving the multipath problem for synthetic aperture radar imaging systems continues, that problem is virtually eliminated very easily by using a laser radar imaging system. So here's an example of what a laser radar or a LiDAR system does better than a radar system, really due to the resolution advantage. In this first image, I'm showing you a simulation of an image of a satellite collected with a 30-meter, pretty large phased array millimeter wave radar system. And so, and this, so this is what the satellite in low Earth orbit would look like into that system. So it's already, a very large array of 30-meter, sort of effectively a phased array of the antennas that are spread out over a 30-meter by 30-meter area. And what you see is you kind of, the satellite, although you can tell there's something there, and it has a little bit of a shape, it still looks like a fuzzy blob, for lack of a better word. Now this next image is an image of that same satellite when viewed through a 1-meter optical telescope that's performing atmospheric compensation. Atmospheric compensation wasn't necessary for the radar, the phased array radar system, because the wavelength's so long that the atmospheric turbulence doesn't really affect the imaging capability of the radar system. However, for at optical wavelengths, small changes in path length due to the atmosphere passing with the light passing to the atmosphere causes optical aberrations and must be compensated for if you're going to form a clean, sharp image of this satellite from a 1 meter diameter telescope. So you can see between the two the detail that's available in the image of the collected with the optical telescope, far exceeds what you can see with a fairly large array of radio telescopes. So and conceivably, if you made the millimeter wave radar array even like hundreds of times bigger, you could achieve similar resolution, but it would come at the cost, extremely painful cost of building such a large array of radio telescopes. So here's an example of something that radar is sort of superior at versus laser radar systems. And this is sort of the classical scenario where radar really shines, is when you're doing a broad area search over a large angle, solid angle, meaning sort of fills a volume of space, and you want to see it's sort of the air defense scenario where incoming aircraft come in, maybe entering the space, and you want to know about it, so you interrogate the space with a radio wave, and then when something bounces back, then you know that you've got an intruder, and of course the time that it took that wave to bounce back tells you how far away they are, and if you've got a antenna that's scanning the space, that gives you some idea, when that's picked up and what direction the intruder is coming from. And to do that this all could be done with laser radars as well. However, the power requirements would be quite a bit higher. Clouds and things like that may obscure the system's ability to see and the target. However, there might be advantages in knowing more precisely where the target is, and so that's why a staggered approach, where you do a broad search to see if there are enemies, and then, or not enemies, but intruders, and then you have another system that more accurately identifies exactly where the intruder is, that uses a laser radar that doesn't have to search the whole space, but can search a small volume in the area where you believe the intruder is. So sort of, a hybrid system could be quite a bit better. And so, this is an example of where, if you're just interested in the broad area search and knowing that there's an intruder there, where radar is superior to laser radar. And the takeaway here is that, radar and LiDAR are different. They're not, one is not necessarily better than the other, or vice versa. They have different strengths and weaknesses, and as I was just saying in the previously, they can complement one another. They can do different tasks that are related to the same goal of detecting and identifying intruders in a wide area search, or um, they could be they could be used together to help identify better what one's looking at in an imaging standpoint, from an imaging standpoint. Um, Basically, every remote sensing application should be analyzed thoroughly to determine which technology is more applicable, or how these technologies can be used together to give a more complete picture of sort of what's going on.